Let's talk about logarithmic functions, because so far we've looked at logarithmic expressions and we've figured out how to solve for different components of those, but let's talk about the actual functions that they can represent. And to start, I want to look at a function that we already are familiar with, hopefully, and that's the exponential function. If you graph the exponential function, hopefully you remember what this looks like. You have a horizontal asymptote on the x-axis. I'm drawing it a little bit above the x-axis just so you can see it, but it should be right on that x-axis. And it gets very close on the left, and then it's just going to shoot up exponentially like that. And it has a y-intercept of 1. Now the reason I want to start with this is because your logarithmic function is actually the inverse function to this, right? Recall that if you want to find the inverse function, you just say y equals 2 to the x, you swap x and y, right? And then you solve for y. To do that here, you could take the log of both sides, but a better way would just be to rewrite this as a logarithm. So log base 2 of x is equal to y, right? Because if you go around the horn, 2 to the y equals x, that's what you have here. 2 to the y equals x. And so your inverse function, f inverse at x, is equal to log base 2 of x. So this function is the inverse of this function, meaning that when you graph it, it's going to be a reflection in the diagonal. So you draw your diagonal line like that, and then you draw your reflection. It's going to look something like this, right? With a vertical asymptote on the y-axis. I'm drawing it a little bit to the right so you can see it, but it should be right on the y-axis. So when you reflect over that diagonal, everything reflects, including the asymptotes. You used to have a horizontal asymptote, now you got a vertical asymptote. You used to have a y-intercept of 1, now you have an x-intercept of 1, right? So while this function up here is y equals 2 to the x, this function here is the inverse, y equals log base 2 of x. Okay? Now, with that being said, we can take a look at some different logarithmic functions with some transformations, because of course transformations play a role in this, right? Just like every other type of function. So I'm just going to make one up here. Different transformations are applied, and they all do the same thing as we're used to, right? Like the 3 on front, that's a vertical stretch. The plus 1 moves it to the left one. The negative 2 moves it down. But when you're actually trying to graph this and you try to move it up, down, left, right, it's kind of hard to see that you're actually moving these things, you know? So the best way to graph these is to find the y-intercepts and the x-intercepts and then actually label them on the graph and connect them together. So if you want to find the y-intercepts, you set x to 0, right? So you'd say y equals 3 log 2 0 plus 1 minus 2. Right, so I set 0 for x. Well, what would happen here? Well, this inside part is just 1 now. So log base 2 of 1, what's that equal to? Well, log with any base of 1 is just equal to 0, because 2 to the 0 is equal to 1. So this whole term is going to become 0, and you're left with negative 2. So that's your y-intercept. For your x-intercept, you set y to 0. So 0 equals 3 log base 2 of x plus 1 minus 2. Now you solve for x, right? Bring the 2 to the other side, divide both sides by 3. 2/3 equals log base 2 x plus 1. You can isolate for x, right? Just rewrite this as an exponential. So 2 to the 2/3 is equal to x plus 1. Right? Just go around the horn. 2 to the 2/3 equals x plus 1, right? Bring the 1 to the other side. 2 to the 2/3 minus 1 is equal to x. And that's equal to approximately 0.587. So if we want to graph this now, we have our x-intercepts and our y-intercept. So let's draw our y-axis, we'll draw our x-axis, and we'll label these points. So the y-intercept being negative 2, that's going to go down here. The x-intercept being 0.587, that'll be about here. That's approximately, right? So you can kind of see based on where these are that the graph is going to be going up like that and down like this, right? And we have a vertical asymptote, of course, right around here that this is getting closer to. The question is, where is that vertical asymptote? Well, the vertical asymptote is located when your graph is undefined, right? And the graph up here, if you look at your original function, ask yourself where this would be undefined. Well, it's undefined when you have a number in here that is 0 or negative, right? Because if this bracket is 0, what's log of 0? Well, if you go on your calculator and try to type in log of 0, it's undefined. You get an error, right? That's because there's no number you can raise something like 2 to get 0 as an answer, right? So to find that vertical asymptote, it's going to be at the location where this is equal to 0. So we can set that to 0, the x plus 1, right? So we'll say x plus 1 equals 0, solve for x equals negative 1. That is the location of your vertical asymptote. So this here is at negative 1. That's where this vertical asymptote is located. Okay, and hopefully that makes sense with the picture. I think it looks pretty good, right? It looks like it's all to scale, right? Decently at least. So that would be how you graph a logarithmic function.